Hi there, welcome back. Hopefully you got to the sound video that the lesson that I recorded for the ISU yesterday in the morning, and then I posted the last night. I did the lab for sound, which is part of the ISU, and hopefully you were able to go into the hub and find the worksheet for the lab, and then again watch the video for the lab, and then do the calculations for the lab, which will also be due with the ISU next Tuesday. And there will be a very similar question on the ISU test next Tuesday to what is in the lab that we did today or last night. So today I want to start into our second topic in the energy unit. In the Irwin textbook, in our textbook, it's chapter 8, but here it's part 2 of the energy unit, which is about thermal energy. Now, to understand thermal energy, we really need to understand matter at its foundation, because in order to understand what we're going to be talking about over the next 5 or 6 notes, we're talking about a direct transfer of thermal energy either to matter or away from matter. So in order to do that, we really need to understand the nature of matter. And I think we've been talking about this all the way back to probably elementary school, but definitely back to grade 9, when we talked about kinetic molecular theory. Kinetic molecular theory is sometimes called particle theory. Particle theory basically says that all matter is made up of particles. Particle theory that says all matter is made up of particles, and that the particles are constantly in motion. It's going to be one of those lessons, I think. Particle theory. Okay, so all matter is made up of particles, and then there's two parts to this. That the fact that the particles are attracted to their neighbors, and that the particles are constantly in motion. Now, if they're in motion, that tells me they have kinetic energy, right? So our understanding of thermal energy in matter really comes back to motion, comes back to the particles themselves. Even the pen that's in my hand, that's not working so well right now, even the pen that's in my hand has motion, it has kinetic energy, not because it's moving around my desk here in my hand, but because the particles that are in the aluminum of the shell of this pen are actually vibrating back and forth. They have motion because of their temperature. Now, when we talk about solids, liquids, and gases, the particles that make up a solid, so again, think about a solid material like a window, like a pane of glass, right? And ultimately, in that pane of glass, the particles that make up the glass are in a fixed position. They're being held, attracted to their neighbors, right? And that force of attraction means they can't go anywhere, right? They're being locked in place. Sometimes they call it a lattice structure. Again, if you get into chemistry in grade 12, you get more into this. But for us, we just need to understand that for a solid, the particles cannot leave their spot. Now, it turns out that I can actually cause the glass to melt. I would do so by heating the glass up to whatever the melting point is of glass. Let's make up a number. Let's say 1,000 degrees. And in order to do that, as I'm heating it up, what's going to happen is the particles that are in the glass are going to move and vibrate faster and faster and faster. So when I talk about a solid, the temperature of that matter is an indication of how fast the particles are vibrating. And those vibrations really are the motion that we talked about, kinetic molecular theory. So the particles in a solid are moving, but they're vibrating. If I heat them up, if I transfer thermal energy to them, they will vibrate faster. They will have more kinetic energy, more vibration, more motion, because they absorbed more energy. Remember, energy can be transformed from one form to another. So maybe I heat up a Bunsen burner, and the energy that's coming off the burning of the fuels, the fossil fuels that are in the gas lines, as the energy from those bonds that's breaking is released, it will cause the glass particles to vibrate faster. So I'm just converting one form of energy or transforming one form of energy to another. Now, what's going to happen at some point is I'm going to get to the melting point of that glass, and as it melts, it will, the particles are vibrating so fast that they can break their lattice organization, their configuration, and that lattice structure that they have, those particles are still held onto each other. There's still that force of attraction holding them together, but not enough that they are locked into their position. So I've given them enough vibration that they break out of their lattice structure, but they're still being held onto their neighbors, which means I can pour the liquid, right? It's now going to flow, right? And that fluidity comes from the fact that the particles are still attracted to their neighbors, but they're not being held where they were in a fixed orientation. Because of that, the particles can vibrate faster as I heat the liquid up, liquid glass. As I heat the liquid up, the particles will vibrate faster. The hotter the liquid gets, the faster the particles are vibrating, and the faster the particles are moving around in 3 dimensions. So they have 2 types of motion. They have a vibrational motion, and they also have a 3-dimensional motion as they are able to zip around from place to place. Now, if I was actually able to heat that glass hot enough, and again, I don't even know what kind of temperature range I'd be looking at, but if I had to get it and heat it enough, I could take that liquid and turn it into gaseous glass. And that gas would basically mean I have not only broken the bonds that were holding it in solid place, but now I'm breaking the particles free of their neighbors so that they actually have no attraction left for their neighbors, not enough that's going to be significant anyway, and they're going to fly around free of each other as they get freed up into the gas state. So I'm actually going to take the energy that I'm going to transfer to them, and I'm going to use it to break the bonds that were holding them together. And then I can take that gas. So let's say it boils, this liquid gas boils at 2,000 degrees and turns into a gas. I could take that gas at 2,000 and I could heat it to 2,500. I could heat that gas to 3,000. I could heat that gas to 4,000. All I'm doing now is I'm making those particles move faster in terms of their vibration and in terms of their 3-dimensional translational motion, where they can fly around in the space at a faster rate, which again is an indication of how much energy they have, and ultimately that's going to bring us to the notion of temperature in a minute. So when we talk about thermal energy, which is what I'm transferring to this object, it is energy, right? So it's measured in joules. And really, the thermal energy in matter is a combination of the kinetic energy, the motion of those particles, as well as the potential energy, which is the energy stored up because of the force of attraction between the particles in matter. So again, let's think about an ice cube now. So I'm going to go out, get an ice cube out of my freezer. I'm going to put it in glass, and I'm going to sit here. I got nothing better to do. I'm home with COVID, and I'm going to watch this ice cube melt. Okay, very exciting. Tuesday night here at the Cinna House. All right, so I'm watching this ice cube melt, and what's happening is as it came out of my freezer at minus 12 degrees Celsius, solid water, ice cubes, and it's going to warm up. Minus 11, minus 10, minus 4, minus 2, minus 1. At minus 1, it's still solid ice, right? It hasn't started to melt yet, and there is energy. It's absorbing energy from the room. So the water particles that are frozen are going to start to vibrate faster and faster and faster and faster. They're going to gain kinetic energy until they get to 0. Now, I know 2 things happen at 0. If I have an ice cube at 0 and I continue to heat it, it will melt. If I take water and I put it in my freezer at 20 degrees room temperature, and it gets colder and colder in the freezer, it's in the ice cube tray, 12 degrees, 9 degrees, 3 degrees, 1 degree, and it gets to 0. Now, at 1 degree, it's still a liquid. At 0, it is still a liquid, but at 0, it makes that change of state. Now, in order to make that change of state, whether it's going from the solid ice cube to the liquid or the liquid water to the solid ice, I'm either adding energy or taking energy away. Now think about what's happening here. Let's go back to my ice cube for a minute. I've got the ice cube, and the solid water is going to absorb energy. The energy is coming from the room, and instead of causing the temperature to go up, it's going to cause the bonds that are holding the solid H2Os together will be broken. Right? So the energy that's being added to the system now, it's not just causing the particles to move faster, it's causing the particles to break free of their neighbors. Right? I'm breaking the forces of attraction that were holding that solid together. So when I'm watching what's going on here, there's kinetic energy, which is the particles moving, but there's also the potential energy that's stored up in matter. The sum of those two is ultimately the thermal energy that we're going to be talking about. So it is both kinetic energy and potential energy, which is the attractive energy. Just like gravitational energy, it's the attractive energy between the particles in a solid. It's also the attractive energy between the particles in a liquid that are still holding on to their neighbors. Right? And I can remember transform that energy from other forms into thermal energy, and then I can cause the particles to either get warmer or maybe change state. Or maybe both. Maybe I take the ice cubes and I leave them on my counter overnight. I come back in the morning and I have 20-degree water. And what happened? I took my ice cube, I warmed it to 0, I converted it into a liquid, and then I warmed the liquid up to 20 degrees. Right? Gaining kinetic energy, changing the potential energy, and then from the potential energy, once it's water, it's going to gain more kinetic energy. So I'm going to add energy 3 times, right? Once to warm it up to 0, once to convert it to break the bonds that were holding it together. Again, just like lifting an object up and giving it gravitational energy, when I break the bonds that are holding the particles together in the solid state, I am giving it more potential energy, right? Which it can gain back by turning back into a solid if I'm going the other way around. Okay, so this look at thermal energy is looking at the combination of both kinetic and potential energy. Now, when we talk about temperature, right? So I often think about this word temperature when I'm thinking about thermal energy. Temperature is a unique quantity because it talks specifically about kinetic energy, right? It talks about how fast particles are moving. So when I measure the temperature of something using a thermometer, right? Remember, a thermometer is telling me, that it's 21 degrees in the room, or 31 degrees in the room, or 11 degrees in the room, right? What it's telling me is how fast are the particles moving, right? Specifically, how fast are the particles moving? If I go from 0-degree water to 0-degree ice, right, I have removed energy from that water to turn it into ice, but the thermometer didn't tell me that I'd removed any energy. Right? It didn't detect a change in kinetic energy because there was no change in kinetic energy. So your thermometer really is a tool that measures the speed of particles. Right? I call it a particle speedometer. And ultimately, all my thermometer is doing is measuring the speed of those particles. Now, some particles will be moving faster in matter, while some particles are moving slower in matter, so it actually measures the average kinetic energy of the particles in matter. Now, to be able to be useful, chemists, physicists, scientists came up with scales, different scales over the years, to look at how much temperature relates to the states of matter and or the amount of energy that's being added. And a number of people have come up with different scales. So von Fahrenheit came up with a scale, which is a temperature scale. And again, I don't really know the history behind why the scale is what it is, but ultimately we know that water freezes and melts. Sorry, it doesn't boil at 32. It freezes or melts at 32 degrees Fahrenheit, and it will boil at 212 degrees Fahrenheit. Now, we know that water for us melts and boils at 0 Celsius, and melts or freezes at 0, and boils or condenses at 100 degrees Celsius. So for us, our range for water is from 0 to 100. On the Fahrenheit scale, it goes from plus 32 to plus 212. Right? So if I say the boiling point of water to someone on this side of the U.S. border, Canada-U.S. border, it's 100 degrees Celsius where water boils. And if you go to the other side of the border into Buffalo, they'll tell you that water boils at 212 degrees Fahrenheit. Right? They do not understand 0 or 100. Specifically because they don't use those terms, right? That when they're watching the news, they will tell you what the temperature is in degrees Fahrenheit, not in degrees Celsius. Right? If I told you that it was 52 degrees Fahrenheit outside, I'd have to think really hard. What exactly does that mean? Well, that means 52 is 2 minus 32 is 20. That's divided by 9 is 2.2. It's 11 degrees Celsius. So I understand 11 degrees Celsius. I understand whether or not I need to be wearing a sweater or not, whether or not I need to be wearing a coat, whether or not I need gloves, right? Whether I need some sunscreen or a short sleeve shirt, right? I understand the degree Celsius thing. I don't really understand Fahrenheit that well because I'm just not used to using Fahrenheit, right? So it's just a different scale. Now, what I know is if I've got water and I boil it, bring it to 100 degrees, and I pour it into a teacup, and I put a tea bag in there, and I know that it was 100 degrees. It was boiling in the kettle when I put it in there, and now it's sitting on the counter, right, in my kitchen. And it's getting cooler as it's sitting there, because I don't want to be drinking 100-degree tea. And I'm sitting here waiting for my tea to be ready, and the tea bag is steeping, tea is steeping, and then I pull the tea bag out. It's still too hot to drink, so I let it cool down some more. And as it's cooling, again, remember, the thermometer would be a way to determine the temperature of my water, my hot water, my tea now. And as it's cooling, the thermometer is telling me that the particles are moving slower. Right? When it gets to 90 degrees Celsius, still too hot to drink, it's cooled from the 100 that it was coming out of the kettle. In other words, the particles have slowed down. And down to 80, 70, 60, 50 degrees Celsius, the particles are slowing down. Thermometer tells me that they're going slower. Right? And as I keep getting down towards 10 degrees, right now it's pretty cold tea, drinking iced tea, and as it keeps getting colder, the particles are going slower until I get to 0. And then at 0, what happens is it changes from liquid into a solid. And there's no temperature change when it changes from a liquid to a solid. It was 0-degree water, and a little while later it will be 0-degree ice solid, and then it will start cooling down, and as a solid ice cube, minus 10, minus 20, minus 30. If I go to Mac and I use one of the minus 80 freezers that they use, that I used to use when I worked at Mac, and the particles just keep getting slower and slower in that ice cube. Right? And chemists ultimately said, well, if I keep getting them slower, how slow can they actually get? I mean, speed, the temperature is the speed. So hypothetically, it will have no temperature when it has no speed. So they said, okay, well, what temperature does it have to be before it has no speed? Well, let's call that absolute 0. That is my baseline for measuring temperature in the scientific world. Okay, and the scale that we're going to use relative to 0, where 0 is my reference point, is going to be called the Kelvin scale. So as I'm doing this, we're going to talk about temperature changes in kelvins. And at absolute 0, particles have no kinetic energy. They have no motion left, right? And that happens, we know, at minus 273 degrees Celsius. Okay, I don't know what that is in Fahrenheit. I don't really care what that is in Fahrenheit. In Canada, we talk about degrees Celsius, and in most of the world, we talk about degrees Celsius, unless you go south of our border. So what I know is if the particles keep getting slower and slower and slower, hypothetically, when they get to absolute zero, they stop vibrating altogether. And we're not even sure what would happen to matter if its particles stopped vibrating, because we've never been able to do it. We've actually been able to get matter down to within 1 degree of absolute zero, but we've never been able to get it to absolute zero, because as long as it's touching something in the universe, which it has to be, it will be absorbing energy from whatever it's touching, and it will never be able to get to absolute zero. So, now it turns out that if I change the temperature of something by 10 degrees Celsius, I change its temperature by 10 kelvins. So whatever the delta T is, difference in temperature in degrees C, it will be the same as the degree delta T in kelvins. Okay, one more time. If something changes its temperature by 50 degrees C, it changes its temperature by 50 kelvins. Right, so 1 Kelvin degree temperature change will always be equal to 1 degree C. So to go from minus 273 up to 0, right, which is with a freezing point of water, right, I'd have to go 273 degrees colder than that to get to absolute zero. So we've got a formula for determining the temperature difference change between Kelvin temperatures and degrees Celsius temperatures, and it says the Kelvin temperature is equal to my degrees Celsius temperature plus 273. So if it is 0 degrees Celsius today, 0 plus 273 makes it at 273 kelvins. If it's 25 degrees Celsius today, which I wish it was, it's not, and I add that to the 273, that would give me a Kelvin temperature of 298 kelvins. Right, so if I look in the samples, the package that we've got in our in the hub, there's 2 sample problems here. The first sample problem 1 says I've got a chemical called ethyl alcohol, and it boils at 78.3 degrees Celsius. That's when it boils. What is the temperature in degree Kelvin? So I know that my temperature in kelvins is equal to my Celsius temperature plus 273, which is 78.3 plus the 273 conversion, and I end up with 281, 351.3 kelvins. Right? That's the temperature that ethyl alcohol will boil. Now, sample 2 here says if I tell you that ethyl alcohol freezes, the same chemical will freeze at 159 kelvins, and what is the temperature in degrees C? Well, if I look at my formula, if I want to rearrange the formula, I can see that the temperature in Celsius is equal to the temperature in kelvins minus 273. I should take my 273 from here across to the other side as negative, right? So I can get my answer here as temperature in kelvins, which is 159 minus 273, and I get 114, negative 114 degrees Celsius. Right. So if ethyl alcohol freezes at 159 kelvins, it freezes at minus 114 degrees Celsius. It's going to be pretty cold before alcohol freezes. And again, there's some sample practice questions for you that you can work on here. As usual, there's a bit of a summary here that takes you through kinetic molecular theory. I would take some time and look through the summary. And I'm going to leave you with the questions that are down here for 2.1, but not question 5 where you have to do some research. So you can just do the other questions, basically looking at temperature versus thermal energy, kinetic molecular theory, and doing some conversions between kelvins and degrees Celsius. Now, I'm not going to finish there. I want to keep on going because I want to talk about, in our textbook, there is a question on page 276, right? And you can work on that question too. Now, so we've talked about 2 words that are related. One is thermal energy, and one is temperature. The other one that we often talk about is heat. And heat basically talks about the amount of thermal energy that is transferred. If I heat something up, I am transferring thermal energy to that object. Right? And heat can also be negative, which we call cooling, but that's the opposite of heat, and it's when I'm transferring thermal energy away from an object, or it's going to have a negative thermal energy. Now, when we talk about thermal energy, if I give matter, thermal energy, then it's going to cause the particles to move faster. If they move faster, they will vibrate faster and harder, and if they're vibrating faster and harder, they're going to push their neighbors. Right, they're going to push their neighbors further and further apart in all 360 degrees in 3 dimensions, and as they're doing that, it will cause matter to expand. So thermal expansion happens as I add thermal energy to matter in the solid state or the liquid state. It will cause the matter to expand. Or if I cool it, the particles move slower and they basically lose that speed that they have. They don't push on their neighbors as hard, and the entire volume of matter will cause it to contract. Right? So we know that thermal expansion and thermal contraction, and contraction of matter agree with kinetic molecular theory because we can cause particles to get faster or slower, and they will push their neighbors further apart. Or less far apart if they're cooling down. Now, there are 3 ways that objects can have heat transfer to them. One is by conduction. Conduction means if a warm object touches a colder object, the speed or the vibrations of the warmer particles will hit the slower moving, cooler particles. And again, you think about a fast thing hitting a slow thing, a fast moving car hitting a slow moving car, rear-ending it. Not a good visual. It'll cause damage to that slow moving car and cause the slow moving car to get pushed, right, to move faster. Right? And what it will do to the fast-moving car is it will cause it to slow down. So what happens is when 2 substances come into physical contact, the warmer ones will be slowed down, the faster ones slow down, and the slower ones speed up. Okay, and then that's how conduction happens. So because there's a difference in the speed of the particles, the faster ones slow down and the slower ones will speed up. If we talk about convection is a way that energy is transferred within a fluid medium, whether it's a solid or a gas. Right? So convection is my second way. The first one was conduction. The second one is convection. Convection means when I heat matter up, let's say in a pot on the stove, right? What's going to happen is the hot water at the bottom of the pot is going to move very fast. The particles will push their neighbors apart. They will become less dense, right, because they're becoming larger volume. Larger volume for the same amount of matter means it becomes less dense, and the less dense will rise up to the top and carry that heat up from the bottom of the pot to the top of the pot. Right, and that will happen in a gas state too. So what often happens is in a liquid or a gas, the heat will always rise to the top, and the cold, more dense stuff will always settle to the bottom. Okay, and the textbook talks a little bit about ocean breezes, the fact that during the daytime the sun heats the sand. As the sand gets warmed up, the air above the sand gets really warm, right, and it will rise above the air that's higher up. And what that does is it creates a gap on the beach where that air has risen, and it pulls air in from over the water. And as it does so, the air over the land rises, the air over the water comes to fill it in, and then we end up with a breeze that's blowing onto the shore during the daytime, and then the opposite happens at night. And again, the textbook spends a bit of time. You may want to have a look at that. The other way of thermal energy transfer is by radiation, and we know that electromagnetic waves travel and they carry radiant energy, and that radiant energy basically can be absorbed by matter, and as it is absorbed by matter, it causes the particles in the matter to move faster. Now, the textbook talks a little bit about thermal conductors and insulators, the fact that some types of matter resist that ability, that they don't accept thermal energy well. When thermal energy tries to go into them, they resist that absorption of energy, and that makes them good insulators. And the things that are good conductors, again, if you go and stir your pot with a spoon, and then you leave the metal spoon in the pot and you walk away from it, and then you come back to stir it again, and you pick up the spoon that's in the pot, even though it's not actually in the soup, the end that you pick up that you go to touch is super, super hot, because the heat travels along the solid, because metals are usually good conductors of thermal energy. So heat will transfer, thermal energy will transfer, which is heat, in good conductors, and then insulators, which are often materials. A lot of them are synthetic materials, plastics, rubbers, things that do not allow for the conductivity of thermal energy very well. And then ultimately, the best insulator is a vacuum, right? Because if there's no particles in the vacuum, there's nothing to carry that thermal energy or that motion through the vacuum, right? And ultimately, things like thermos bottles and other types of insulated containers have got either gases in them that do not transmit energy very well, or might even have a vacuum in them, and the vacuum means it's not going to allow for thermal energy transfer. Now, ultimately, because even for a thermos bottle, if you've got hot soup in there and you go to drink it, you put the soup in at 7 in the morning before you go to work, and then at noon you go to have your soup and it's still nice and hot. By morning the next day, you find your soup's lost some of its energy because of its contact with the plastics and the other materials that make up the thermos bottle. So again, in the samples and homework package here for section 2.2, there's a summary here, right? And then there are some review questions, and I'm going to leave you to work on those. When we come back to this tomorrow, we're going to get back into some heat capacity, which is starting to use our calculators again. But for today, we're not going to be using our calculators. We're just trying to understand this whole notion of thermal energy. So you may want to read the textbook pages, sections 8.1 to 8.3. That starts on page 252. Again, it goes through the three different scales, the Fahrenheit, Celsius, and Kelvin temperature scales.